So today we're going to be looking at solving the wave equation now, and we're going to do that using the separation of variables method. So let's solve the equation gradient squared u over gradient, partial squared u over partial t squared equals c squared partial squared u over partial x squared. And let's set our boundary conditions and initial conditions. So for our boundary condition, we'll look at fixed ends for now. So u of 0 comma t equals 0, and u at L comma t also equals 0. Next, our initial conditions. So we'll say that at u of x comma 0 is equal to f of x, and u prime at x comma 0 is equal to g of x. The reason we need two functions for describing the initial conditions compared to our heat equation is because we're looking at the second derivative with respect to time, so we'll need two initial conditions with respect to time. And okay. So now what we'll do is we'll write u as a function phi times h. So phi of x times h of t. The reason we do this is because we know there has to be some function out there that can be solution out there that the variables can be separated like this. So we'll figure that out first, and then we can generalize it using linear combinations. So this equation can now be rewritten as phi times d squared h over dt squared is equal to h times c squared d squared phi over dx squared. Rearranging this equation, we get 1 over h c squared d squared h over dt squared is equal to 1 over phi d squared phi over dx squared. Now, one thing you'll notice, these two expressions have to be constants because this expression, when you change it with respect to x, is constant, which means this equation, if you change it with respect to x, must be constant. And likewise, if you change this equation with respect to t, it must be constant. So if you change this equation with respect to t, it must also be constant. And we'll call this constant negative lambda, which means that we can then rewrite our partial differential equation as now two ordinary differential equations, d squared h over dt squared equals negative lambda h c squared and d squared phi over dx squared now equals negative lambda times phi. Next, so now what we do is we just have to solve these two ordinary differential equations, and these are solved differential equations, which means that we can just use their solutions as are known. So the solution, we'll start with the top one. The solution here is just h equals c sub 1 cosine of ct root lambda plus c sub 2 sine of ct root lambda. How we get this expression, so is using ordinary differential equation methods, but basically lambda, there's three different solution cases for whether lambda is less than 0, greater than 0, or equal to 0, and this is the solution case for when lambda is greater than 0. And yeah, for lambda greater than 0, it looks like this, whereas with lambda is less than 0, it is an exponential function. When lambda equals 0, it's linear. And so for the wave equation, this solution makes the most sense, which is why we're using it. Next, we have to do, next we have to solve the second equation, phi equals, because these are in this two, say, have a similar form, their solutions are also going to be a very similar form. So we can write this, c sub 1 cosine of x root lambda plus c sub 2 sine of x root lambda. But unlike the first equation, we actually have some boundary conditions we can label for phi. So when we did separation of variables, we can now rewrite these two boundary conditions now as phi of 0 equals 0 and phi at L equals 0. And so we can solve using those boundary expressions. We can now solve for lambda and for one of these constants. So we know that when x equals 0, phi equals 0, and if we plug it in, well, if we plug in 0 here, cosine of 0 is 1, which means that for this expression to be, and sine of 0 is 0, which means this expression cancels, but c sub 1, for phi to equal 0, c sub 1 has to equal 0, which means this expression cancels out, leaving us with phi equals some constant c times the sine of x root lambda. Now we also know that phi equals 0 when x equals L, and so if we solve for that, that means 0 is equal to sine of L root lambda, or L root lambda equals n pi, where n is some integer. This means we can solve for lambda equals n pi over L whole squared. And we can plug that into our h equation up here to solve for h. And if we now combine multiply phi and h, we can get a complete expression for u, which is u is equal to u is equal to a sub n, call it a sub n, sine of n pi over L, sine of n pi over L x times cosine of c n pi over L times t plus b sub n sine of n pi over L x times cosine of c n pi over L t. N pi. There we go. Cool. Now, to get the general solution, all we need to do is just realize that because the wave equation is a linear operator, that the solutions are just a linear combination of this solution. So we can just say that generalize u by doing this. And now what we have to do is we have to solve for a sub n and b sub n, because we know that u is just an infinite series of this expression. The way we solve for that is using our initial conditions. So u equals this function, and u prime is equal to u prime equals the sum from n equals 1 to infinity of now a sub n times cn pi over L sine of n pi over L x times sine times negative sine, I guess, of cn pi over L t plus b sub n sine b sub n cn pi over L sine of n pi over L x times cosine of cn pi over L, or sorry, not cosine, sine, because the derivative, this should be cosine, and this should be sine. Miswrote that. But yeah, cosine of cn pi over L t. Now, what we can do is we can plug in 0 for t and rewrite these functions from f of x and g of x. So f of x is equal to, well, if we plug in 0 for t, if we plug in 0 for t here, or sorry, not for t, yeah, if we plug in 0 for t here, this cancels out because sine of 0 is 0, and this reduces to the expression sum from n equals 1 to infinity of a sub n sine of n pi over L x. Similarly, if we plug in t equals 0 for the second derivative, we get g of x equals, well, sine of 0 is 0, meaning this expression cancels, leaving us with a sum from n equals 1 to infinity of b sub n cn pi over L sine of n pi over L times x. Nice. Now, to further simplify this and separate the coefficients a and b, we can use certain trigonometric orthogonality identities. So the way we do that, we multiply both sides by sine of n pi over Lx, f of x times sine of n pi, or sorry, not n, m pi over Lx, where m is just some integer just like n. And that equals the sum from n equals 1 to infinity of a sub n sine n pi over Lx times sine of m pi over Lx, which you can put over here. And now what we do is we can integrate both sides from 0 to L with respect to x. And what you'll notice is that this expression equals 0 when n doesn't equal m, but when n equals m, this expression becomes L over 2, which means we can rewrite this as the integral from 0 through L of f of x sine of m pi over Lx dx equals a sub m times L over 2, or a sub n is equal to 2 over L integral from 0 through L of f of x sine m pi over Lx dx, right? And then what you can do is you can just do this integral for every single value of n that you have, and you'll be able to solve for that coefficient. You can do a similar thing for b, and you'll get the coefficient, the expression b sub n is equal to 2 over b sub n is equal to 2 over c n pi, 2 over c n pi integral from 0 through L g of x sine, and this should be a n, not an m, sine of n pi over L x dx. Wonderful. Let me just sine of n pi over Lx. Awesome. Cool. And so this is the solution now to this right here is the solution to the wave equation, the complete general solution to the wave equation for these boundary conditions. And one thing we can do is we can now interpret a little bit what's going on. So inside this infinite summation, we have this thing called this expression called the normal mode, right? Normal mode. What the normal mode is it's one wave. It's one wave in an infinite sum, and we have some names for some of the constants here. So a sub n squared plus b sub n squared is the magnitude for this normal mode expression, and it's called the tensile force. Likewise, Cn pi over L, the constant that appears inside the cosine and the sine, is called the circular frequency. Right there. Circular frequency, which is the number of waves in 2 pi units of time. Right? So what that means is that for, say, n equals, for n equals 1, sorry about that, for n equals 1, there will be this normal mode will just be one wave with some magnitude, right, from 0 through 2 pi, or if when n equals 2, you'll have a circular frequency of 2, so there'll be 2 waves of some magnitude, and or for n equals 3, 3 waves, and so far. And if you sum all of these different what's called standing waves, you will get the infinite series, right? Because what you'll notice is that these waves, they're called standing waves because all they do is they just move with respect to time, and they don't change. They don't change in magnitude. So, for example, what that means is that if you rewrite, for example, if you rewrite the expression sine of Cn pi over Lt sine of n pi over Lx, which is the expression here, right? Right here. You can rewrite this as using a trig identity, you can rewrite this as this expression. Half of cosine n pi over L x minus ct is minus half of cosine n pi over L x plus ct, right? Where this is a standing wave traveling to the right, and this is a standing wave traveling to the left. And you can do a similar thing with cosine, where you just replace the cosines here with sines when it's cosine of Cn pi over Lt times sine of n pi over Lx. Then you just replace the cosines with sines in this expression, and you get similar thing where you have two functions where your expression can be described as your expression u can be described as the sum of two functions, one going to the right at x minus ct and one going to the left at some x plus ct. Cool. And so that's the solution to the equation and a little bit of interpretation of what it means. Next we'll look at this wave equation, generalizing it to other boundary conditions and what those mean. I hope you enjoyed the video. Thanks for sticking around, and please like and subscribe if you enjoyed.